So we will start lecture 3 here, that is our Eutectic system, and this is also known as binary Eutectic system. So as it's in name, binary word is there, means this is also a two component system. Okay, now in this we will take two minerals that are diopside and anorthite. So as you can see in this graph, suppose we have a bulk composition of A, okay, and this curve here, this one, it is a liquidus, this curve here is liquidus, and this is a solidus. So when this bulk composition A start to crystallize from the melt, it will hit this point, okay, and in this point we will get a composition of pure anorthite. In this we will get the composition of pure anorthite, not like in case of the binary solid solution case. Okay, so again this the composition will be pure anorthite, and this curve will move in this direction like this, and this will move again in this direction, and then it will hit this point. This point is known as eutectic point. Okay, after this point, after the further crystallization, the diopside will start to crystallize from the melt, and it will the melt will be out of the system. So you will get only the diopside and anorthite, and this curve will move along with this in this direction, and the final composition will be of this 70% anorthite and 30% diopside. Now if we want to calculate the degree of freedom at each and every point here, so here the degree of freedom will be equal to 2. How we will, if we apply the formula F equal to C minus 5 plus 1, so number of component will be 2, as it's a binary eutectic system, and there will be only one phase. So if we apply the formula this one, we'll get it out to be 2. The degree of freedom here two phases are there, so degree of freedom will be 1 in this case. In the eutectic point, if we calculate the degree of freedom, number of component is 2, number of phases will be 3, diopside, anorthite and liquid. So 2 minus 3 plus 1, so it will be minus 1 plus 1, it will come out to be 0. So at eutectic point, the degree of freedom is 0, and this point is also known as invariant point. Now if we want to calculate the composition of melt and solid at any point, for example this point E here, we will apply the lever rule. Now this tie line we will draw like this, and suppose if you want to calculate the fraction of liquid present, so we will go toward the solid side, that is this one, EF by total DF, as you can see in this formula. You can calculate the fraction of liquid melt here. Similarly, if you want to calculate the fraction of solid, we will go toward the liquid side, so it will be DE by total, that is DF. And the fraction of liquid by solid, if you divide this as equation 1 and this as equation 2, if you divide both of them, you will get this formula. Now one of the most important thing here is that if the bulk composition is on the right side of this graph, okay, so you will the first solid to be crystallized is plagioclase, and after that diopside will be crystallized later. So this lath of plagioclase will be surrounded by pyroxenes. It will be surrounded by pyroxenes, and this type of texture is known as ophitic texture. Now if the bulk composition is on this side, let's say B composition, the curve will move like this, and in the start you will get the pure diopside composition, that is this one. Here also you will get the pure diopside composition, and then you will reach the eutectic point. After that melt will disappear from the system, and we will get the diopside and anorthite like this, and here the solidus will move along with this, and the final composition will be of this. So if the curve, if your bulk composition is on this side, we will get the another texture in this. What will happen? This diopside, that is our pyroxene, is surrounded by plagioclase, and this type of texture is known as subophitic texture. Both ophitic and subophitic textures is very common in case of dikes, and we'll see these textures in case of dikes. Now if you see the reaction here, so this is our liquid 1 here. Here this liquid 1, if you move on this side, this liquid 1 is giving us liquid 2 plus solid. That solid is of pure anorthite. Okay, so what we'll get, liquid 1 is giving us liquid 2 plus anorthite. Okay, now reaction at eutectic, if we have seen the graph here, like diopside anorthite, if we have seen the graph, so in the eutectic point, here, the liquid is completely getting disappeared, and below that we are getting diopside plus anorthite. So liquid is completely disappearing and getting converted into diopside plus anorthite. So this will be reaction at eutectic point. This will be the reaction at eutectic point. Now these textures I have discussed. If the uh, augite, that is your pyroxene, form before the plagioclase, means we are at the left hand side of the figure, means we are at this side, we will get the subophitic texture, and if we are on the right hand side, means your plagioclase, that is anorthite, which is formed before the diopside, then we will get the texture which is known as ophitic texture, means this one. Okay, this is the ophitic texture. When the bulk composition is on this side, we'll get ophitic, and if the bulk composition is this side, we'll get subophitic texture. Now this everything which is happening here is in case of equilibrium crystallization. Now in case of equilibrium melting, what will happen? Suppose our bulk composition is this one. This one is our bulk composition. Okay, and we will start to melt this. It will reach here at this point, and then it will directly jump to the eutectic point, where we will get our first melt. Okay, here we will get our first melt. Then depending upon the composition, if your like in this, the initial composition of the rock is rich in anorthite, so this curve will move toward the anorthite direction. So we'll get liquid 1 here, then here liquid 2, and like this we will move up to the this point, where the bulk composition of the solid is equal to the bulk composition of the liquid. So both should be equal in this case. So reaction here will be diopside and anorthite at point, will give liquid at point D. Now in case of fractional crystallization, what happens? Whatever crystal which forms will be removed. So if we see this example like this, here the first crystal which forms is a pure anorthite, and you are removing this pure anorthite from the system. We are removing this pure anorthite from the system. So it will, graph will go on this side and this side like this, and whatever crystal is forming here is getting removed like this. This crystal which forms is getting removed, and this curve will hit this point, which is known as eutectic point, and the final rock which we get will be of the eutectic composition. So final rock which we get is of eutectic composition in case of fractional crystallization. Now in case of partial melting, means whatever melt is formed, that melt is getting removed. So suppose this is the initial composition of the rock, and when we hit this point, we'll get the melt of this composition, and whatever melt which is forming here is getting removed. So whatever melt is forming here is getting removed. So liquid is getting removed until the point the dioxide is finished. So when the dioxide is finished in this rock, we will get the final melt, which is of pure anorthite. So the composition after the dioxide is completely finished, the composition will directly jump from point X to point Y. Means from here the composition after the dioxide is completely finished, it will directly jump from here to here. So there will be no intermediate path in this case. So this ends our lecture on the binary eutectic system.